Welcome back to the second lecture of the Sage and Computing and Other Stuff course that several people will be teaching over the course of this term at the Institute for Math and its Sciences in Chennai. This is the Sage Introductory Programming Tutorial. I'm calling the next one the Advanced Programming Tutorial, but it's really just the second part of the Introductory Tutorial. But nonetheless, the things that we'll talk about today are going to be fairly introductory. They won't assume that you know anything about programming, although they will assume a certain amount of, I guess, mathematical maturity in the sense of being able to pick it up reasonably quickly. And once again, I should acknowledge that it's based on some tutorials prepared for a Math Association of America workshop funded by the National Science Foundation. So let's get started. We have a couple more students coming in, and presumably some of you online will be joining us as well. Willkommen zu den Deutschland. And let's take a look at what we have. So first I wanted to take a look at the homework from last time. So this is not my computer, so hopefully I won't open some crazy things. So students, how many people did all the homework? Raise your hand if you did all the homework. Oh, okay, that's about half the class. That's not too bad, I guess, for an ungraded course. I mean, I hope the part where you found some topics in the combinatorics directory was fun. You should find somebody else. Was there anybody who really had an interesting mathematical piece of information that they found, just some really interesting mathematical concept that they found, or was it all trivial stuff? Like I did the homework, right? I found the de Bruijn sequences. So
I found a nice thing that I had contributed to Sage.
Oh, well, that's good. See, you can contribute yourself, so that's pretty useful. Nobody else found anything interesting? Lie algebras or no? Are we all set? Yeah, I'm okay. Did anybody have any trouble calculating an integral? I didn't give you the command, but you had trouble? No trouble. Okay, great. Okay. I really don't care if you know how to solve a Sudoku in Sage, but it's just fun to know that you can do something. There's also a Rubik's Cube solver. Anybody know Rubik's Cube? The cube that you move around. Yeah, so that's kind of fun. More seriously, how many graphs there were of a certain order or of a certain order in size, and I guess it turned out maybe not everybody knew what all these things were, but it's stuff that you can look up in the documentation. So I'm just curious, was that fairly straightforward to find a command to find all graphs with a certain number of, in this case, vertices, 5 vertices, or was it hard to find that? Was there in fact a command? Yeah? Mm-hmm.
Took the list of the graph and
What's that?
we took the list of the graph and
You took the list of the graphs and just printed it out. Right, so you can list all the graphs. So there's a way to do things like list all graphs, right, of a certain size. And then for the order, you might have to do something a little more clever, and today we might, or next time we might talk about that. Oh, there is. Oh, great. See, I didn't even know. I thought maybe someone would try to learn a little program ahead of time. So see, there's different options that you can use. And so getting the graphs, and maybe can you give me the command for that? I can try it out in a...
uppercase G, R-A-P-H-S, so that's the class, I guess.
Okay. Yes.
Oh.
So we're going to try using the Sage cell server and see if that works. So,
Graphs.
oops, hang on. This is not my computer. Graphs 5 probably.
Yeah.
Dot.
then list of.
Oh, okay. So we can list that.
And then
Oops.
oh, maybe there's a dot list. Huh?
Ah. Len list. It's not, the usual keyboard things aren't working. Oh, I have to accept the terms of service. That's right. Okay, name error. Graphs is not defined. Okay.
Small g.
Okay.
Oh, is it?
Ah.
Small.
Whoops. Yeah, this is not my keyboard, so I get confused by it.
Sometimes I found that it stops if you just click on that box.
Yeah, I just
No, the box, the output box.
the
Click
out,
on the output box.
the outward box.
Output box.
Output box. Oh.
Oh.
No, not this time. That's
Maybe
okay.
that's just a coincidence.
It probably was. So
you have a Sage server, by the way. So
yes, I know. I'm in fact on it. I was just trying something a little bit different just to see. But we can always, I'm trying to figure out how to use this guy. I might have to.
This keeps happening.
I might have to reload. Well, it is coming all the way from,
Well, there's a lot of things on.
Yeah, that never works for me also. It just takes a
It
lot.
worked on my mobile.
maybe there's just too many graphs of some.
No. Just did it.
And then you were saying that there's an optional argument as well?
Order equal.
Order.
Uh,
Oops. Or sorry, size equals.
Sorry, size equal to.
Oh yeah, size.
So in principle, this should do it. There you go,
Oh,
6.
yeah.
Okay, so sometimes it just, is flaky. Okay, so there are 6 graphs with 6 vertices. Sorry, 6 edges and 5 vertices. Okay, that's kind of interesting, right? Because if you try to do it by hand, you might miss one, right? It's kind of hard sometimes. So let's take a look at a couple other homework problems. Let's see. Compute the sum of all the primes less than 2 million. Did you get the right answer? I think you're allowed to check the answer on Project Euler still, right? They can't create and count anymore. Did anybody get the right answer, they think? Yeah, good.
149,138,9.
Okay, so 149 million, something like that.
Yes.
Okay, sounds about right to me. The point is that you might have to do something a little bit different. In order to compute the sum of the primes less than 30, I can do that by hand, right? 2 plus 3 plus 5 plus 7, up to 29. But to do it up to 100, now probably most of you can get all the primes up to 100 fairly easily and add them on a calculator or something. Up to 1,000, I believe there's 124 primes less than 1,000. So that's all starts to be very tedious. You could do it. I have the number theory book I teach out of has a list at the back of all the primes up to 1,000. But up to 2 million, you probably had to start learning about some other programming construct. And we'll talk about that one today. Again, same thing with calculating the determinant of these diagonal matrices. This isn't hard. They're all 1. But can you get Sage to do it for you? And the bigger it gets, the more tedious. So Dilpreet, what did you do?
If I first matrix, then M dot determinant is 2.
But so you did it separately for each one. You made them diagonal matrix 1, 1, 1, 1, 1, 1, 1, 1. Right. So the question is, can we do that more easily, right? And it turns out we can. Okay, so, and I won't ask about question 10. The main point of this was just to make sure that everybody had a chance to try out some stuff. So what we're going to do now is we're going to mostly focus on matrices just because it's something everybody's familiar with, but it's also a little more advanced than just plotting functions. But the lessons apply everywhere. So whatever we do, we're going to talk about different programming things, but just think about the kinds of objects that you care about. Again, most people here are thinking of algebraic combinatorics, so that's the kind of thing you think that you care about. But if for some reason you really care about analytic number theory or whatever, or in my case, a lot of strange geometric things, whatever you need, you can apply the same properties. So the first thing I want to do is review, actually. Ready? So we have these methods. Okay? There was this dot notation that we explored last time. And so I want to just review how that works and show you a couple of useful things just to kind of get us warmed up. So let's remember how to make a new matrix. I'll do Shift-Enter again, and it's pretty easy. I just put each row inside brackets, and then I put the rows themselves inside brackets. So it's lots of commas and brackets and things, and you have to be very careful because you have to put all of that inside of a parenthesis. So that's kind of annoying, but it's still better than some other programming languages which cause you to use brackets and parentheses in ways you don't in math, whereas here, matrix, it's a function. Okay, so parentheses. Anyway, so that's pretty straightforward once you've done it a couple times. Because you guys know what rings are, you'll notice that we get different answers if we use different rings. That's not really too germane to what we're doing now, but I especially like if you do the ring, the field of 3 elements, 1, 2, 3, 4 becomes 1, 2, 0, 1, right? So Sage knows what to do. And in fact, if you checked what the 0 was, it won't be 0. It'll be the identity element of the field of 3 elements. Okay? It's going to know the right thing to do. So that's not really programming, that's just math, but it's useful to know that as we go through. This print statement is also kind of useful, but we won't use it a lot. Okay, so anyway, give things names. Always useful to give things names because then you can reuse them, right? Just like in math, let G be a graph. So we're going to give it the name A, and then I do A and it comes down. What can I do with the matrix? So this is what we're going to remind ourselves from last time. Of course, you can apply a function to it, and in one case, the determinant function is available. You can just do det of your graph, or of your matrix, and that's great. It has to be a square matrix, of course. But what if I wanted a row-reduced echelon form? Okay, I'm assuming you've all done echelon forms ad nauseum. So if I do r tab, well, I think if I do r tab, this is, again, always the danger of using something that's not your computer, is you don't know what's going to happen. Oh, there they are. Okay, so there's lots and lots of stuff, lots of random things if you want them, in fact. Random quadratic forms, random trees. I wonder if a random tree will give you the zero. Maybe it will, or maybe it won't give you the empty graph. We were talking about this last time. And lots of other stuff, including the Robinson-Shenstedt stuff that you were talking about earlier, last time. So anyway, the point is none of these things are row-reduced echelon form. So that's not a built-in function. But Sage knows that A is a matrix. It knows it's a square matrix. So it's going to know that you can do an echelon form on this thing. So you have to think of a method. This is how I like to think of the methods versus the functions. When you're doing matrices in linear algebra, of course, a matrix is just a thing, right? And you can multiply two matrices. Or you can multiply a matrix by a vector. But then you learn that matrices are also linear transformations, right? And then it makes more sense. Well, do you multiply it on the left or on the right? So if you multiply it on the left, it's sort of like, the transpose of doing it on the right. And sometimes doing it on the right makes more sense because you're kind of applying it afterward. But then you have to think about how your bases are arranged and everything, right? It's different. You don't get the same answer as when you multiply on the left and on the right. And so that's kind of the way you want to think about this. Is it's sort of like, is it a group element or is it a linear transformation? And I'm going to argue that the methods you should think of as being like linear transformations, right? You're applying some transformation to it, but you do it on the right because that's just one way we do matrices. If you don't like that analogy, don't use it. But it might be helpful to some of you to think about that. Okay, so the gory details are you type the name of the object, so that's A in this case. Then you type a dot for this object-orientedness. And then you type the name of the method, which in this case is also det, because it just is. And then parentheses. And if there was like super determinants, then you could say det type equals super on the inside. But there is no such thing as super determinants. So it's just det, and we get -2. And this object-oriented notation, as I said last time, is this really big advantage because you can only do the things you need. Later in this course, when you have a computer science person come in, they're actually going to teach you how to create your own methods. I'm only going to teach you how to create functions. But you will be able to create your own methods using what are called Python classes. And so that's pretty exciting. And some of you have already done that perhaps, and you have. So yeah, you can make your own methods to things. And that's really awesome because then it'll only work for the stuff you care about. And in this case, I only want a row-reduced echelon form for a matrix. And what do you know? The rows are linearly independent, so I get the identity matrix. Any questions about why that's the identity matrix? Everybody remembers their echelon forms, right? No? Maybe? Okay. If you don't, then look up echelon forms. Remember, keep the parentheses. This is just the way Sage works. Some of you may be familiar with a programming language called Ruby. Ruby doesn't make you keep the parentheses, but say Sage and Python do. And we already talked about this last time, so this won't work, and I won't bother you with it. We did it last time. Now, the reason this is useful is because of the tab key, right? And so what can you do with a matrix? You can do lots of things. And we already talked about them last time. Oops. And what happens then is you have some surprises sometimes, right? So subtle changes in an object will give you different things. And this is why the method notation is so important. Because here, the echelon form, you might think, oh, if this is just like, a command, this is just going to give me the same echelon form. Let's see what echelon form gives me. 1, 0, 0, 2. Why? Anybody know? It's up there too, but Why is the echelon form of 1, 2, 3, 4 1, 0, 0, 2?
Integer.
Integers. Right. In order to do a Gaussian transformation or Gaussian elimination on this, to get 1, 0, 0, 1, you're going to have to multiply this row by 1/2. And 1/2 isn't an integer. And the matrix as I defined it, I only had 1, 2, 3, and 4. And Sage was smart enough to say, oh, those are all integers, so this matrix is going to have to be an integer matrix, and hence I'm not allowed to. This causes no small size of problems in undergraduate linear algebra courses, of course, which is why we have the RREF method, so that you don't have to worry about stuff like that, because you don't want to introduce, for me, at least in America, you don't want to introduce first semester linear algebra people to rings. But maybe we should, but we don't. So how could I fix that? Well, it turns out behind the scenes, Sage is saying this is in a Z matrix space. So what I can do is use a different method to change the ring of coefficients. So let's change it. And look, it's a different method. A dot change ring to QQ, which is Sage's shorthand for rationals, right, quotients. And then let's look at the echelon form of B. And if I do that, now I get what I want. But the reason this is in the programming tutorial, not the math tutorial, is because you see, A dot change ring gave me a different matrix. It gave me something else. It did not change the original matrix. You might think A dot change ring would change A, but it doesn't. You read the documentation, it gives you a new one. This is the subtleties that you have to be aware of. And so having the method notation and having the documentation is going to help us with that. And if you don't believe me, I'll do the echelon form of A, and A is still the same.
But sometimes things do change when you.
Sometimes they do change. That's correct. Right. So that's the whole point of this. Is we're doing it slowly, but it's subtle, and you have to pay attention to what could happen or might not happen. Okay. Any questions? Yeah. No. Okay. So let's take a look at another thing. Do we need an argument? So here's a question. If I wanted to get a column vector, do I need an argument? Let's take a look at A dot column, and if I tab that, it looks like, it looks like, yes, A dot column, and then it says I. So it looks like I do need an argument in there, and if I take a look at the examples, sure enough, A dot column 1, A dot column minus 1, what? Minus 1th column? That doesn't make sense. So let's input 1. Let's see what happens if I get A dot column 1. 2, 4. Okay, so I got a column. Nice. So since I got a vector back, now I can even take that vector and take the dot product of the vector with itself. Look at this. A dot column 1, that's 2, 4. And I'm going to dot product. I'm going to dot product it with itself. What's 2, 4 dot product 2, 4? Yeah, 4 plus 16, which is 20. Okay. So see, it works. This is a really useful thing. We call this chaining methods. It's like composition of functions, right? A dot column 1 dot product, and you can do it like 3, 4, 5. There are some people when they're trying to simplify really complicated algebraic expressions, they chain 3 or 4 simplification methods of varying safenesses, and by safenesses I mean, sometimes they do things like ignore branch cuts and stuff like that, all in the goal of making some huge expression simplify to E or something like that. So it's kind of fun. But the point is that you can keep doing this as long as you know what you're going to be doing. So again, the method thing is very helpful because you can keep on doing that. All right. So did anybody notice, by the way, that 2, 4 is not the first column of A? It's the 1th. Wait. But I put 1. What's going on? So in order to explain this, we have to take a little detour into what are called lists, and they're going to be very useful, as you'll see in just a second. But it turns out that that is the right thing. Don't worry. Sage did not have a bug where the first column. This is the 1th column, which is not the same as the first column. Like many programming languages, Sage begins numbering of anything that's like a sequence at 0. Let me repeat. Numbering begins with 0. Sort of like the guest house I'm staying in right now. When I came in at 3:30 in the morning 2 days ago, The guy's like, oh yeah, and you're on the first floor. 503 is on the first. First of all, 503 is on the first floor? Wait. That didn't make sense to me. But I was like, okay, I'm going with it, right? And then we get in, and the guy takes my suitcase and goes up the stairs. But first floor. Okay, so the first floor, and actually in Germany there is a difference as well between two different ways of numbering floors where the first one is just not given a number. But I wasn't expecting that. But now that I know, oh, the 0th floor is where the reception of the TV is, and then the first floor is my room, and the second floor is where some of you are staying. So this is what's going on with lists in Python. Anything what you do in Python should be numbered by zeros. Point, gap numbers starting at 1. For those who have used gap, I know, right? Is that right, Dilpreet? So yeah, you just have to make sure you pay attention to that. Most programming languages start at 0. Some do start it with 1. Okay, so why is this important and useful? What we're going to do is we want to create lists of things in order. And so here's a list of some decimals.
So
3 point, yes.
Here in column 0 we should define to get the first.
That is right. So if I go back up and do column 0, absolutely, great point. So if I do column 0, oops, first I have to get to it. Not my computer. 1, 3, okay?
In column -1?
We'll get to that. We'll get to that. We're not there yet. We'll get to that.
-1 in the second column.
Shh, don't give it away. Don't give it away. -1 is not the second column. It's the -1th column. Okay, so here's my list, and you can see I'm comma separating various decimals, 3.1. And I just think of a list as an ordered set. Whoops, that is not the one. Here's the one I wanted. And you see Sage says that they're real numbers, so it adds a lot of zeros to make sure you know it's an approximation of a real number. We'll talk more about that next time, what that really means. All right, so I have these 4 things, and yeah, it's just a list. It's an ordered set. Think of it as an ordered set. Multi-set, an ordered multi-set, right? You can repeat things. All right, but I can put lots of things in here. So here, you can't really see it because of the size of this screen, but take a look at this list, my list. 2 is the first element. Ranujan is the second element. And this is in quotes, and you guys will perhaps have a little exercise in the homework to what's up with those quotes. And then look at the third element of the list. It is itself a list. I have the 1th column of A, and the number of partitions of 9, remember that from last time, and 5. So the third, or the second, depending on how you count, element of this list is itself a list. So anything can be a list, pretty much. Now, what happens when I access these guys? Just like with the matrix, if I take the 0th element of the list, I get 2, which is the first thing, right? But we call it the 0th. If I take this second element, I get Ramanujan, and then so forth. Now, somebody who is clever, or snide, or something, was asking, what about the -1 thing? And you might say, there's no -1, right? But this is actually some very useful behavior. There's the -1th element of my list. Okay? So in your homework, you'll be asked about it. Yeah, somebody said it, but I won't. Try and figure out what it is. Experiment a little bit. Try it with different lists. My list 3, okay, it doesn't wrap around. Okay? This is also very useful, actually, because what it means is that you can go through something when you're doing something very complicated, and you can basically say, when the list runs out of stuff, don't do any more stuff. Okay? So this is a really useful thing. All right, there's lots of advanced stuff that you can do with lists, but we're not going to do a lot of them. Here's just one small tidbit, but next time we'll talk more about more advanced things you can do with lists. I just want you to know what a list is. Okay, now what we're going to do with the list is something useful. What we did so far is not useful. This is just what a list is. But let's get back to thinking about all the stuff we want to do. The whole point, I think, of doing the computer, not the only point, you can do other things. Kanapan is going to be giving you a talk about experimenting and exploring in mathematics using it. But one thing that's really useful for math and computers is doing tedious things, such as computing determinants of powers of matrices. Right? If you do it by hand, okay, I guess you can use the theorem about determinant of a to the I, but it can be very tedious. So let's take our matrix 1, 2, 3, 4, and first let's make some powers of my matrix. And there they are, right? Of course, I had to do a lot of typing to do that, right? I had to type A to the 0, A to the 1, A to the 2, A to the 3, A to the 4. So instead of doing that, I'm going to do what's called a loop construction. And here's where the lists first come into play. What I'm going to do is I'm going to look at all the powers 0, 1, 2, 3, and 4. I'm going to print a to that power. You can think of this as mathematical. For each, the word each isn't in there, I in the set 0, 1, 2, 3, 4, for each of those I, give me a to the I. Does that seem like a reasonable kind of notation? There are many notations for lists, for loops like this in computer programming language, but it seems kind of reasonable. For any I, yeah, we're used to the math simplification notation. For all I in 0, 1, 2, 3, 4, it's a set. Give me a to the I. Okay? And that's exactly what it's going to do. Oops, except it did a little extra thing for me. So there they are again. A lot less typing, and it's more organized, because now if I wanted to add 5, all I would have to do is go up here and do comma 5, right? Whereas before I might have had to do something very complicated and then cut and paste some huge thing and then replace the 5. And that would be very boring. And also liable to inaccuracy. Nobody wants inaccuracy. So the square brackets created the list. The powers of the matrix come in the same order as the list, and this is called a loop. You will have to practice this. There's homework. I do want to point out that the syntax is extremely important here. It's important in any language. In Python, the syntax is composed mostly of white space. So I'm going to show you 2 different things that aren't a list, or aren't a loop. Here I have for I and 0, 1, 2, 3, 4. And you see how the colon here is missing? Invalid syntax. Okay? Sometimes you can even see if it'll tell you exactly where it was the invalid syntax was. But maybe that helps you, maybe it doesn't. But at any rate, it's invalid syntax. Okay, what about this guy? This guy looks good. He's got a colon, right? He's all set. Indentation error, expected an indented block. So Python was smart enough to know that we should have been indenting. And if you go up to the actual one, you can see that there's an indentation as well as the colon. That's the structure of the syntax. You guys know how important it is to be careful about things like that. If you've never programmed before, just think of this as, how in an early proof class, you're always expected to prove that everything is associative and commutative, and then later on you don't, because it just becomes second nature. And you're just like, yeah, it's obvious. But at first, your teacher makes you prove, is this a group? Show it's associative. Right? Even though it can be very boring to do so. So that's what you should think of this as. Usually we use 4 spaces here, but that's a convention. As long as your indentation is consistent, it doesn't matter what you do. You just have to always do the same. Yeah, you can use any number of spaces, but the 4 spaces is the visually most pleasing, most people find. People get quite religious about issues like this, so I don't want to open.
Getting errors.
No, as long as you're consistent, right? You have to always use this. If you have different numbers of spaces, that's bad. But if you always do the same number. Yeah, so this is going to come up a lot more when we do more advanced material, but today. So there's quicker ways to do this. I did the long way because it's best to learn that way first because it's the most flexible. However, in certain circumstances, there's lots of shortcuts. So if you only want integers, Sage has this little notation, which I believe comes from Maple. But people liked it so much that they implemented it in Sage. So 0, ... 4, there you go, 0, 1, 2, 3, 4. Range 5, you might think that would be 1 through 5. So let's just take a look at this guy. See what I get if I do this. So I'm taking the determinant of these powers. Determinant of the identity is 1. Determinant of the original matrix was -2. 4 minus 8, 16. 0, 1, 2, 3, 4th powers. Oh. So range 5 started at 0 and ended before 5. That's okay. That's the definition. That's the definition of range. I don't pretend to defend it, but that's how Guido, the originator of Python, decided to do Python, and he's the ruler, so he gets to choose. So the point is that if you have something simple like that, there are some shortcuts. So you don't have to type 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that'd be very silly. So, but not for everything. There are some better shortcuts too. If you want to skip, so if I wanted to go from 3 to 23, but not including 23, with a skip of 2, then I could use this. And then this is another way to achieve the same thing. And notice this one ends in 21 because this is a Sage construct. This is a Python construct. So one of your homework problems is going to be get the determinants of all the even powers of A up to 14. Okay? So you have to combine the things we just learned to do this. But the point is the loop idea, right? For everything in a certain list, a certain iterator, if I'm going to be technical about it, so here's the canonical form, then whatever is here, do it. But you do it that many times. And if one of the times it's not possible to do it, then you'll get a nasty error. Okay. Oh yeah, one final very minor comment. You can do these things with more complicated Sage things using something called srange, but I'm not going to talk about it. But for some of you, that may be useful to know, because range only does Python ints, and srange does fancy Sage things, you know, like real numbers and stuff like that. Yeah.
For example, if you want to factor a number, and you just said 3 not
That-
factor, it would work. Whereas when you randomly
Yes.
n not factor,
Yes. So yeah. So Kanapan is pointing out that a fairly subtle thing that the integers here are not the same as the ones here, and we'll show you this in the following way. I dot factor. Oh, okay, fair enough. There you go. Okay. But if I do this, and now I'm going to change this to 1 comma so we don't get that problem. Int has no attribute factor. So that's a very subtle thing, which I'm going to now make sure I erase all trace of from the worksheet so that no one gets confused by that. But yeah, later on, that's the kind of thing that can definitely happen. Good point. Now that I've confused everyone by doing that example. No, seriously, that's a really good point. What you can do depends on what you have, right? And so you have to be careful about that kind of thing. All right, now back to lists. So it's fun to print out all the determinants, right? But seriously, what am I going to do with just like a printed out list of determinants? I'm going to hand it out to my students or something. I'll put it in the newspaper. But what I really want to do is do more stuff with it. I want to do more mathematical things. Maybe I want to check if all the determinants are divisible by 2, which in this case they were, right? I might want to check if all the determinants have some other property. If I'm not doing determinants, but I'm getting groups as my outcome. I might want to check if all those groups are solvable or simple or something like that. So I need to get it back as a data structure. So what we're going to do is we're going to combine a loop with a list method to do something. So the first thing I'm going to do is create an empty list. And that's just bracket, bracket. So that's an object. It's a thing. It's a list with nothing in it, right? So you guys know all about that. Now what I'm going to do is I'm going to do for I in range 5. So again, from 0, 1, 2, 3, 4, colon, white space, L dot, so lists have methods too, not very many, but they're very useful ones. L dot append the determinant. So let's see what that does. Whoop, let's see what that does. There. No, it created a list with all the determinants, and now I can use that list. Right? Now I have something that I can really process, examine. Maybe I save it if it's a very long one. I have done, there was this one computation I was doing when I first started using Sage for research, which was after I started using it in teaching. And when I had finally, waited for 24 hours for this thing to finish computing, I was so scared I would lose it that I immediately saved the object. There's ways to save objects in Sage, and the syntax is save, unsurprisingly. And then I backed it up and everything because I was so worried I was going to lose this monstrous file to make sure, So this is really useful, right? Basic lists don't have a lot of methods, but this is a really helpful one. And you can do whatever you want with these guys.
So indentation you didn't change for print.
Yep, for this and then, but print is separate, right? I didn't want to print L each time. So watch, this is going to be very, very. Watch this. If I just do this. And notice that it's the same L, so it appended them to the original L. Yeah, so there's 2 things that happened here. The first thing that happened is I had already created L, and it was up through there. So then I did it again, and so it continued appending. So I got them all twice by the end. Secondly, because this is inside the indented block, each time it printed 5 more times. Yeah. So this is subtle, right? Programming is hard. It's not as hard as math, but it's still hard. But once you start figuring out what to do with it, you can figure out how to do it. So it's very nice that you can do this. And I think I like that example. Yeah. So Shiva, I might actually add that to the worksheet before I publish it. Which reminds me, you should all know, those who are on campus. This is only available to those on campus. If I go home now, there is now a Sage server, which is set up. It's Citron:8080. So if you're on campus, you can go to that location, and I already published the one from last time. So and then you can go to it, and you can edit a copy of it. It's really nice. So, yeah, so Citron:8080, and you can start trying out stuff. But don't do it for too many, because we don't want to overload the server. But yeah, so it's fun stuff. Good.
So you can create an account on it.
Yes, that's right.
You should create an account.
You should create an account.
Maybe that can be the homework.
That can be part of the homework. I can easily add that to the homework, now that I know it's available. Okay, well, we have one more thing to talk about with lists, and then we have to talk about defining new functions, and then we'll already be done, because it's already 10 after. Okay, so believe it or not, this is going to be tedious too. It may not seem tedious now if you've just seen this for the first time, but trust me, it will be tedious. So Python supports something even cooler called list comprehensions that are kind of like set builder notation. You're familiar with this notation, right? N squared, the set of n squared such that n is an element of the integers and 3 is less than or equal to n is less than or equal to 12 set. We've all done this. But it turns out that I can almost directly translate this into what's called a list comprehension. Bracket, that's like a set, n squared for, there's that line, n in, and then instead of z, you just say 3.12. And that's it. That's all I have to do. Wow, that's a lot more concise and doesn't have this pesky indentation to deal with. So think of it mathematically, and you can just do this really powerful thing. And again, it's nice because it's all in one line. Right? It's a one-liner for getting all the perfect squares from 3 squared to 12 squared. It's sort of like turning the construction of the loop around, actually. Right? Instead of starting with 4n between 3 and 12, you end with it. And then instead of ending with n squared, you put it at the beginning, and then there's the brackets. But you can use this in lots of places. So here's a plotting one. We're not doing a lot of plotting in this course, but I just can't resist plotting x to the n for n between 2 and 6. So this is really nice. Right? Oh, it's too big. Help. That's because I zoomed in so much. So there's all your x to the n's, right? It's really nice. Here they are.
It should be separate.
What's that? I plotted them all together. So it's possible for me to plot multiple functions at the same time. And so that's what I did. It's fun.
So you give a list of functions and plot
Yes.
them all together.
Yep, I gave it a list of functions.
It said
and it
for
plotted.
n in this plot, then it would have created separate.
Yes, exactly. That's right. Or I could have added them together. But we aren't focusing on plots, so I'm not going to. But yeah, plot can take a list of functions. So here's our determinants again. Man, I should have just showed you that, right? But I don't want to do that until you understand what a loop is. All this is doing is kind of internally creating something like this. And I found this example for, well, it's not that exciting, but that's just because this is the example of a finite file group. And here's the reduced word for each of the semi-group generators of the group. Because every group is a semi-group. Yeah, so you can do it for anything. And there it is, list comprehensions. Now, I want to show you an application of lists before we get on to defining functions. This is not strictly about programming, it's about visualization. Remember, mathematics, especially proof, is largely about communicating math to somebody else. Everybody knows a story of somebody who had this awesome result on paper and nobody could understand it. Oh wait, that was Perelman's proof, right? And so, so there's like all these huge books that prove the Poincare conjecture and the geometrization conjecture, but Perelman's papers are not the same size as all those things. So communication is part of what we do. The same thing happened to Lobachevsky, right? He published in this really, really obscure journal, and then hardly anybody knew about non-Euclidean geometry until a couple decades later. We want to be able to visualize and advertise. So I'm going to make my list of determinants, and here I'm going to actually make a list of lists. I have I and the determinant. So you see how I'm making a list, 0 determinant of a to the 0, 1 determinant a to the 1, 2 determinant a to the 2 for each of the numbers from 0 to 4. Okay? Now what I'm going to do is I'm going to put them inside the table command, and I get a table. Not very exciting, but it's a table.
If you do LaTeX tables, does it,
Well, it's funny you should ask that, Omri, because to make it look nicer in the notebook, so this works only in the notebook. It does not work in the cloud currently, and I told William about this. HTML table, now it looks nice. You see it even like every other row is kind of highlighted, so you can see what it, and of course this is just eye candy. There's not math here. But it's very important for being able to, especially some very long things that you're trying to get across. I like doing this when I have students kind of try to experiment on finding patterns for things like divisor functions. Even better, I can make a header line. So here I'm going to have a table. I squared is the first list. 1, 1 is the second list. 2, 4 is the third element of the list. And then I'm going to put another one of these keywords. Remember how when we did the numerical precision of pi, we said prec, digits equals 20 or something. So this is header underscore row equals true. And that means I want to make a header row. And there it is. Yeah. And I think you can use CSS to change the colors and stuff like that if you wanted to. So so this is very nice, right? And then in the homework, I'm going to ask you what happens if you put a $sign on either side of the I and on either side of the I squared. Don't say, but it's your homework. But some of you can already guess what will happen if I put a $sign there. It's really fun. It's just great. Okay, questions about lists and things like that? Well, we have our final topic, and it's a big one. It's all about just making Sage bigger. That's all. Not a hard thing. So there is this thing about functions. Look, if I really wanted to, if I just wanted to get a matrix square minus the matrix, I could just type in the name of the matrix and then do it. A squared minus A. And then if I had a different matrix, I could just go up here and change some of the numbers, right? I could do that. So let's change the number. Let's change that to 1. Oops. There. Tedious, right? I mean, this is ridiculous. Why would I keep doing this? Plus, it's going to be hard for me to do anything really useful with it. So what we do in Python and Sage, and in any computer language really, is we do what's called create a function. And here I'm going to create a function called square and subtract. And the conventions in Python and Sage just use underscores. You can't use spaces. So that's just the way you do it. But if you wanted to do something else like square and subtract and no underscores, that's fine. And this is going to make a new function that's going to square and subtract. Look at the syntax. Instead of for I in, that's what we had for loops, def space. Here's the name that I want to give the function. I'm going to give it a good descriptive name, square and subtract. That's pretty good, right? And then I'm going to say my matrix, but it doesn't really matter what I call this. This is a dummy variable. Right? Just my matrix. Colon, space, look familiar? Colon, space. Right? So indentation and colons. And then I'm going to return, this is also a special reserved word in Python. I'm going to return, I'm going to give back to the user my matrix squared minus my matrix. Some functions don't return stuff, but the ones that we want to talk about do. In one good Python introductory test, he calls them fruitful functions. So let's see what happens if I use my function. Are you ready? I'm scared. Let's square and subtract A. It worked. And I can square and subtract other matrices. So let's take the matrix 1.5002. Listen, if I square this, I get 2.25 and 4. But if I subtract, the original matrix, I should get 2 again. Why do I get 0.75? What's 1.5 squared? Isn't it 2.25? Oh, right, minus 1.5. Yes, okay, good. So it works. What do you think? Could this be useful for speeding up your work to make a function that does stuff? Jillpreet's giving me good feedback. Yeah, this is awesome, right? That's because she has some experience with computer programs. But you will love it once you do it. Technical point. This is a Python function, not a Sage symbolic function like here. That's a good thing, actually. I don't really want this function to be something I can take the derivative of. I mean, you could, but I personally right now don't want it to be a function that I could take the derivative of. I want it to just be a thing that does stuff. I need a function that turns off all cell phones. Now, you might wonder if you're worried about what the function does. Okay? So these are all just little things about functions. I think, honestly, square and subtract, I hope that this is pretty good. But just in case you forgot what square and subtract means, could I make my own documentation? Answer, yes. Observe the indentation rule and just put triple quotes after the definition but before the return. Return a squared minus a. Okay. Sounds good. Let's see what happens if I try to tab complete that. Oh, yeah. Look at that. It's even typeset nicely. That's because of the backticks. They do LaTeXing for you. So you can start now, today, in your homework, creating your own functions to do. I mean, of course, simple things like squaring, but also hard things that you care about right now in your research. You can do them, put some documentation, and then it's ready to send to somebody else. Right? You're explaining yourself. One of the worst things that happens in computer programming is that people don't document enough. They don't tell you what they're doing, even within, like, why did you do this thing? And then you have to think about it. It's sort of like the speaker, there's some step that seems obvious to them in the proof, and you're just sitting there thinking, why does this work? Why does this work? And then they say, oh, it's because it's a right-angled arc group. And then all of a sudden you realize why it was trivial. And if you want to make crazier documentation, this is great. Here's the documentation for Bessel functions in Sage. And it's going to take us a second to typeset. And you can see you can make arbitrarily complex things in the documentation, right? Hypergeometric functions, all kinds of crazy stuff. So all kinds of fun differential equations. Anyway, so that's not that important, but it's just worth knowing. Now, there is a little note here. Again, we have to be subtle sometimes. Who says that my matrix had to be a matrix? Unlike in other programming languages, Python is what's called dynamically typed. So you can put anything into my function square and subtract, which is good because I might want to square and subtract the square root of 5. That's something that can be squared and subtracted, right? On the other hand, remember this G, which was some Weyl group? Yeah, I can't subtract. I can multiply two elements of a group, but I can't subtract two elements of a group. It's not a ring. So you have to be careful, right? That's the danger of defining a function as opposed to a method. But again, we won't cover that until someone comes in to talk about object-oriented programming. So you just have to be a little careful. There's lots of flexibility. I am not going to show you at this time what these things do. I want you to look at them in your homework and see what's different about them. Each of them is different from the functions that we've defined. See, this one has two things in there. This one has two things and an equals sign. What the heck? This one has one thing, but then there's two things that it returns. But there's a comma. So you have to figure out what those things mean and how they work. And there's some good resources out there, and those are just some that I know about. And so in your homework, there's one where I ask you to actually, after you've analyzed these, to create your own function, a simple function that uses them. Again, if you've done a lot of programming, this will be very easy. If you haven't, it may be a challenge. But once you do it, you'll see how useful it can be to be able to have some flexibility in how you do functions. Okay? So that's functions. So let's see, what have we done? We talked a little about methods. We talked about lists and loops, which are very useful. And then we talked about functions. And you can imagine that now at the end, I'm going to combine them all to create a function that takes lists and loops. But I'm not. You guys can do that. Instead, I'm going to give you a couple gotchas. And then we'll take a look at the homework. So I don't know, is gotchas, is this a phrase that you're familiar with in Indian slang. So in America, a gotcha is like, oh, gotcha. You know, it's a little trick. It's something where you thought it was really obvious and easy, and then somebody said, oh, no, this is actually really hard. Or I guess, well, it's easiest to do by example. So here's a gotcha. It's like, I gotcha. I got you. I is the square root of -1. In Sage, I'm not kidding. In Sage, the square root of -1. Okay, which one? Yeah. We don't answer that question. It should be that. But 4. Apparently, the square root of -1 is 4. How is this possible? I did define I equal 4 before. Where did I define I equals 4? Does anybody remember? Yeah? Who did? In which list? Do you remember? Oh, yeah, he's looking at the worksheet right now. Great. Taking the powers, right? I said that the powers of A were A to the I. Right? Do you remember? Yeah, so of course I is now 4 because that was the last power I did. In fact, as I say here, when was the most recent time it happened? I did it about 10 times earlier in the worksheet. So, valuable lesson. Anytime you use a name, it may be renamed. Again, in some programming languages, this is not the case. They'll give you an error. In Python and Sage, it's not an error, and that's a good thing, I think, because we want flexibility. Again, it depends on what you're trying to do. But most of the time with the math, it's not so much about optimizing everything for speed, but it's about actually getting anything done. Math is hard. You want to actually try and experiment as soon as you can. So you have to have some flexibility like this in order for that to happen. Luckily, it's okay in this case. Anything that was predefined in Sage, I can restore. So once I do restore I, we get I and I squared are I and -1. Good. Again, it doesn't answer the question of which square root of -1. We choose some embedding into the complex numbers. All right, there's another problem that you can have. This is very subtle, and this is the last thing we're going to do today. Because of this dynamic typing and weird, subtle things can happen that are not intuitive to mathematicians. If you've done a lot of programming, this is something you'll know about. But if you haven't, it took me a long time to understand what was going on here. And at its base, it's really about some very low-level computer stuff. So here I have a matrix, 1, 2, 3, 4. And then here what I'm going to do is I'm going to say B equals A. Now, the last time we did this, we said B was the matrix with a changed ring, so it really was another thing. But in this case, I just want to have 2 names for whatever reason, maybe just for convenience. Believe it or not, this actually has made B and A refer to the same matrix. There's a word is in Python. If you say B is A, it will say true. They are the same exact object. They're not just equal. The computer thinks of them as exactly the same. So the problem is that if I change A, let's say I want to change the 0, 0 element, and I haven't talked about the syntax, but we'll talk about it next time, to be 987. Whoops. Now B has also changed, even though I didn't tell it to change B. So that's kind of subtle. If I want to get around that, there's a thing called copy. And now the copy, which C is a copy of it, that's a new matrix, and that one is 1, 2, 3, 4. So that one's okay, but the other one's changed. And this is just a subtle thing. Okay? I didn't have to use the command show, by the way. That was just because I wanted to tell LaTeX. That's kind of fun, but I won't mention that. Suffice it to say that it's probably safer to let each equals sign stand for one thing and avoid some redundancy. But you just have to be aware that subtle bugs can creep in because of these programming things, and every language just has to make a decision about them. It's sort of like the convention that as you go to the right, x gets bigger. Who said? Why couldn't it be the other way? There's an office of someone at our university, and she has this map of the world where south is at the top and north is at the bottom. Okay, it's supposed to blow your mind because you haven't thought of things this way. And for a mathematician, I'm like, seems okay to me. But of course, there's this enhanced prestige to United States and Russia, these huge countries at the top. And then countries close to the equator are really small, and they're further down, places like India, right? So the idea is to get people to think differently. I don't know if it's effective or not for changing points of view, but it does show that there are some things that are just conventions. This is a convention. Python could have done it differently. But now that is the convention, we have to be aware of it. Okay? And there will be many things like that you will encounter over the course of this course. Okay, so let's take a look at the homework. If I can get this to scroll properly. Okay, first homework, there are these quotation marks when I made the table. Where's my thing here? With I and I squared, and I want you to learn about them. Okay, that's not hard, but it's just learn about them. I already asked you about this question. This one I think is really a good example for you to do. Look, there's some tutorials. They're very basic that some people created with me about groups, graphs, number theory. Just pick something and something you can do to it. And then just find a way to list everything and then do that thing to it. So for instance, can you list all the elements of a finite group and then get the order of all those elements? Okay, two-step process. Same thing, can you write a function that does that? So for instance, given a group, can it return the order of the group? Add some documentation. So you could call it, order of group or something like that. This is just some stuff I want you to figure out how to do just to continue trying to find out how to do stuff. Block diagonal matrix, you get a character table, stuff like that. In the notebook worksheet, and we'll post this on the course website, there are some exercises about getting determinants. I just want you to do that. Here's your function homework. Define a function. Sorry, this thing is hard to scroll. Define a function that inputs a matrix and returns a determinant of the cube. And then here's find a function which inputs a matrix and a power and returns that power. Okay, so this is a little harder. So maybe I should reorder this. Maybe question number 12 should be before questions 7 and 8. And that's the one about func 1, func 2, and func 3. A couple Project Euler things that'll be kind of fun. You'll probably want to use lists, maybe functions as well. Read about deep copy. This is actually subtle and important. You should be able to think of a mathematical setting where you would need this. This is probably the hardest question, actually. Read about. But it's a very subtle thing. And so I think it's the hardest one. And I think that's almost it. Final one, this is a preview of next time. Here's a way to numerically integrate in Sage. It gives you the answer and an error bound. How can you get just the answer to the numerical integral or just the error bound? So I hope that these are interesting. I'm going to rework on this as soon as we're done here, and then we'll post it up. So it'll be published on the server. Again, this Citron:8080 for those who are on campus only. And then we'll also post a PDF of it, and the video at some point will also go up on the YouTube channel. So thank you very much.